And for a sinusoidal input, our forcing function now is going to be a sinusoid with a frequency omega and an amplitude a. This means that I can write that second order differential equation like this, with my coefficients 1 over omega n squared, 2 zeta over omega n, and then that static sensitivity once again times f of t, which in this case is a sine omega t. Similar to my first order system, I'm going to get a response that has some transient, which I'm not going to care about in this sinusoidal response. We cared a lot about that in the step response, and it will be fairly similar. I'll have underdamped cases, overdamped cases, etc. In this case, what I'm really interested in is what the response of the steady state signal looks like. For the step response, it was very simple. It was just that Ka, right? But in the sinusoidal example, I'm going to have a sinusoidal output that's going to have a different magnitude in a different phase based on the input frequency. So this part right here is going to be my steady state response. So at long time, after a fair amount of time when the transients died down, this is basically what I'm going to get from my output y of t. And I have, in this case, a magnitude change. I can effectively think of a 1 in the numerator here that's dependent on frequency. And I have a phase change also dependent on frequency. So that magnitude ratio, m of omega, is going to be 1 over the square root of, this is fairly complex, so 1 minus omega over omega n, that omega over omega n squared, that whole thing squared, plus 2 zeta omega over omega n squared. The phase is going to be the negative inverse tangent of 2 zeta omega, that should be omega over omega n, divided by 1 minus omega over omega n squared. So I could rewrite this as y of t is my transient response plus Ka, right? That static sensitivity and the amplitude of my sinusoid is going to influence my magnitude response, right? So that multiplied by the magnitude ratio is going to give me my actual magnitude of the output, sine omega t plus that phi of omega, right? And that magnitude ratio are defined like this. The phase response is defined like this. And similar to the first order system, I can plot a Bode plot for that magnitude ratio and that phase response. In this case, I'll also have 3 cases like I did for the first order system. And I'll start with omega over omega n is a lot less than 1, or I could rewrite that as the frequency of my input sinusoid is a lot smaller than the natural frequency of my sensor. And in that case, this term right here is really small. Omega over omega n is negligible compared to 1. And this 2 zeta omega over omega n, since that term is also squared, that one is also going to be negligible. So in this case, my magnitude ratio at these low frequencies is just going to equal 1, or if I'm thinking of this in dB, would be 0 dB. My second case would be when omega over omega n equals 1, or when omega equals omega n. And in this case, this term goes to 1, this term goes to 1, right? So this subtracts from this one right here, so this term is 0. So I just end up with 1 over the square root of 2 zeta squared. So it'll be 1 over the square root of 2 zeta, or 1 over 2 zeta. Or in dB, this would be minus 20 log of 2 zeta. So you can see how the damping ratio is going to influence the Bode plot of the second order system as well. And then finally we have the case where omega over omega n is a lot bigger than 1, or the frequency of my input signal is a lot higher than the natural frequency of my sensor. And in this case, we effectively have an omega over omega n to the 4th term here, and an omega over omega n squared term, and some other squared terms, and this 1 term. Well, because this omega over omega n is very large, so say something like 10 or higher, then in this case, the omega n over omega n to the fourth term is going to dominate everything else. So basically this goes away, and I'm left with this omega over omega n squared, square root of that, that whole thing to the fourth and square root of that. So my magnitude ratio is going to be 1 over omega n squared, or I could write this as omega n over omega squared. And in dB, this will be minus 40 log of omega over omega n. Okay, so let's plot this magnitude ratio response. So I filled out the magnitude ratio portion of my Bode plot. I have frequency, and I'm using a log axis for frequency to compress as many frequencies as I can on the plot. And I'm putting everything in terms of omega n, right? Because we have this omega over omega n factor that we're looking at. And what this says is that at the low frequencies, low input frequencies to my sensor, I don't get any kind of change basically in my my magnitude ratio is just 1. So that's saying basically at this point right here, omega n over 10 and below, I'm at 0 dB. All right, I'm doing this axis in terms of dB. All right, and then let's look at the higher frequencies as well. So in the case that omega is 10 times omega n, right, my magnitude ratio according to this would be minus 40 dB. And similarly, if omega is 100 omega n, then my magnitude ratio should be minus 80 dB. So based on that, I can start plotting some points here. So I'm at minus 40 dB for that 10 omega n. For 100 times omega n, I'm at minus 80 dB. So I've got some kind of slope going on here. And that slope, in this case, is minus 40 dB per decade. And you probably remember that the first order system, I had a different slope for that roll-off. In that case, the slope was minus 20 dB per decade. So that's a really good indicator if you're looking at a Bode plot, if you're looking at a first order system or a second order system. Second order system's always going to have that minus 40 dB per decade roll-off. And then what this middle term here is telling me, when omega equals omega n, and this is related to the damping ratio, is I might get a little bump in this curve if I have a particularly small damping ratio. So say I have a damping ratio of about 0.5 or so, then I'll get a small little bump here, and this whole thing will kind of go up and then go to that minus 40 dB per decade slope. So that was a damping ratio of about 0.5. If I had a much smaller damping ratio, say of 0.05, then I'm going all the way up to 20 dB in this case. So in this case, I have something that's going up like this and then down to that minus 40 dB per decade slope. Right? And I'm going to keep getting these higher peaks with smaller damping ratios. So if you have a resonating system, typically you have a very small damping ratio and you have a very high peak in this frequency plot. Right? Similarly, if I have a larger damping ratio, I actually don't end up getting a peak, but I still have that minus 40 dB per decade slope. So this might be something like a damping ratio of 0.7. So the key differences between the first order magnitude ratio and the second order magnitude ratio are the roll-off. So second order system, I had minus 40 dB per decade in contrast to minus 20 dB per decade. And the other thing is that with small damping ratios, at least, I can get a magnitude response greater than 1. In that first order system, I could never get a magnitude response greater than that 0 dB there. I can analyze the phase response similarly. In the case where omega over omega n is a lot smaller than 1, or omega is a lot smaller than the natural frequency of my system, in that case, this is going to be a very small number here. So my phase is going to be 0 degrees. In the case where omega over omega n equals 1, or omega is equal to omega n, in this case I'll have 2 zeta this will go to 1 right here, so I'll have 0 in my denominator. So I'm effectively taking the inverse tangent at infinity. So in this case, my phase will be minus 90 degrees, or minus pi over 2. And then finally, omega over omega n is a lot bigger than 1, or I'm at a very high frequency input. My phase in this case is going to go to minus 180 degrees. So in this case, I know that for these low frequencies, I'm at 0 degrees on my phase response plot. At the higher frequencies, say an order of magnitude above omega n, I'm at this minus 180 degree point down here. And in the middle, at omega n, I'm at 90 degrees. And so a typical plot might look something like this. But the sharpness of that transition is going to depend on my damping ratio once again. So I'll have a very steep transition at smaller damping ratios. So as I go in this direction, as my damping ratio gets smaller. I get a steeper transition there for a smaller damping ratio. And if I compare this to the phase response for a first order system leveled off at high frequencies at minus 90 degrees. Second order system adds an extra 90 degrees. So I'm now leveling off at minus 180 degrees. And at that natural frequency, I'm at minus 90 degrees. So there's a good tell, once again, what order system I'm at as to what the high frequency phase for that system is. Okay, and a quick reminder of why we care about all of these sensor dynamics. If I have a sensor, right, or system dynamics in general, if I have a sensor and I have some kind of measurand that I'm trying to measure, maybe it's a pressure in a car engine, for example, and it has some oscillatory response, a sinusoidal response, and the input's going in like this. So this is in units of, say, pascals. Let's say that sensor has a sensitivity in volts per pascal. It's giving me a voltage output based on a pressure input. Now, the other thing that sensor might be doing is giving me some phase and amplitude shifted version of that input. So maybe I'm at a very high frequency relative to the natural frequency of the sensor, and so I get a really attenuated response at the output. Now, it's the same frequency, right? So the same period that I have in both cases here, but the attenuation can be fairly significant and can impact my reading. I can also get a delay in my reading, and so the phase shift could also impact what I think is going on in the system that I'm trying to measure with my sensor. So the most important point out of this is that you need to pay attention to the frequency content of the signals you're trying to measure relative to the parameters of your sensor. If you have a first order sensor, tau, that time constant, second order sensor, you're looking at the natural frequency and the damping ratio of the sensor.